So we're going to have a look at the first 6 questions in the past paper and booklet for Lattice enthalpy. The subheading for these questions is Group 1, Group 7 Bohr-Haber cycles. All that means is that these are questions kind of based upon the first basic Bohr-Haber cycle we looked at in your notes in the third video. For example, sodium chloride, which is Group 1 and Group 7 compound. As we're going to look at later on in the booklet, you can get some slightly trickier Bohr-Haber cycles involving things like Group 2 and Group 6 elements, which have slightly different Bohr-Haber cycles. But we're just going to concentrate on getting your head around the standard basic style of question that could come up in the exams. So obviously the mark scheme's at the back of the document, so check that obviously yourself. But this is just going through and explaining a bit more detail of the thought process behind each question. So first question is kind of maybe the most basic kind of style of question. You're given a big table, given lots of information about this compound cesium chloride. Remember, cesium is this Group 1, so it's not too far from sodium chloride. You're given a partially completed Bohr-Haber cycle. It gives you all the different stops on the journey, but the first 2 parts of this question. First part is actually matching up what energies correspond to which change, and then finally calculating the Lattice enthalpy of cesium chloride. So trying to keep sense of this, because obviously it doesn't look exactly the same as the ones you got in their notes, but I always start with the solid ionic salt there at the bottom right. So going along the right hand side, that's transitioning to cesium plus ion in the gas state and the chloride ion in the gas state. That would correspond to the Lattice enthalpy, which is A. Going around the other way, normally we go from the elements in their standard states turning into the compound. That's known as the enthalpy of formation, forming 1 mole of the compound from its elements. So that would be, looking down, enthalpy of formation would be F. Now going around the other side of our cycle, we're going from cesium as a solid to cesium as a gas. That would be the atomization of cesium, which is B. And then we're transitioning cesium gas into the cesium plus ion with an electron left over. That'd be the first ionization energy of cesium, which is D. We're then splitting up our chlorine molecules into single chlorine atoms. Again, this bit always have to be careful about. We're forming 1 mole of atoms, therefore that is still atomization of chlorine, which is the energy we've got in the table, so that is C. Now by elimination we can tell this is E, but just to check, we're putting that electron from the ionization energy back into chlorine, forming Cl-. That's the electron affinity of chlorine, the first one, which would give it the letter E. So if all that's said and done, we have to calculate the Lattice enthalpy of cesium chloride using our Bohr-Haber cycle and the numbers in this table. Again, you could just go straight away, you might be very comfortable with this, but just to give a bit of extra working out, I'll probably transfer numbers onto this cycle, just to help me keep track of everything that's going on. So this is the one I'm trying to calculate, that's my unknown. My enthalpy of formation is minus 443. Cesium's atomization is plus 76. Its first ionization energy is plus 376. The atomization of chlorine is plus 122. And then the electron affinity of chlorine is minus 349. So I have to get an alternative route from cesium chloride solid to the gaseous ions, going up. Therefore I have to go this way around the cycle. Just checking my arrows, most of them are in exactly the correct configuration, apart from the formation one as normal. I need to flip it to get the cycle going the correct way around. So I'm going to go this way, which involves putting plus 443. So the final sum is just going to be adding all those numbers together. Again, you might think it's very implicit about what you've done here to the examiner, but it's always good to put it as a calculation line just in the real exam. So I'm going to put the delta lattice enthalpy equals plus 443 plus 76 plus 376 plus 122 plus minus 349. Type in the calculator and that ends up with being plus 668 kilojoules per mole. On to question 2, which is a multiple choice question. Which one of the following chlorides is it not possible to construct a Bohr-Haber cycle? So they're clearly all something chloride. The key distinction here is that for Bohr-Haber cycles we're talking about lattice enthalpies. You can only have a lattice enthalpy if you've got an ionic lattice. So the odd one out here is one which isn't actually ionically bonded, it's actually covalently bonded. Silver chloride is metal non-metal, rubidium chloride is metal non-metal, magnesium chloride is metal non-metal, HCl is 2 non-metals bonded together. That's a polar covalent bond, it's individual molecules, not a lattice, therefore we can't construct a Bohr-Haber cycle. Question 3. Which one of the following reactions in the Bohr-Haber cycle for potassium iodide is exothermic? So that's kind of just a wee bit of revision from your definitions on the first page of your notes. Just going down step by step. This one here, going from solid to gas, that's the last enthalpy. It's always endothermic. We're breaking apart a lattice. This one's the first ionization energy of potassium. That again is endothermic. It takes energy to rip that electron away. This one is the atomization one. Strictly speaking, it's the bond dissociation enthalpy of iodine, breaking 1 mole of bonds. Again, we're breaking bonds, that takes energy. And the final one, that's gaining electron to iodine, forming the iodide ion. That's adding an electron to a positive nucleus. That's favourable, it's electron affinity. Therefore, it's an exothermic process. That's our answer. Question 4. Slightly different style of question here in 2 different ways. One is you're not given the whole Born-Haber cycle. And moving on a little bit, you see the actual final calculation where we've already been given the last enthalpy here. We're asked to find a missing formation enthalpy, which is a kind of standard variation, just manipulating our cycle in a different way. But coming back to the first one, part 1, complete the empty boxes. Just have a look at what we've been given so far. Again, I'd always start on the bottom here. One clear change is we're going from something up to our gaseous ions. That's almost certainly going to be our salt itself, which is rubidium chloride. Must always put state symbols in a Born-Haber cycle. RBCl as a solid. Then we're forming that from the elements, that's enthalpy of formation. Then we've got our 3 steps going up to get to this Rb plus, Cl and E minus. Again, my first step probably going to be atomization because I need to turn this solid into a gas. So I'm going to do that as one step first. So Rb gas, keep the chlorine the same. Then I'm going to turn my rubidium into an ion by doing ionization energy. So that would get me Rb plus gas plus a half, sorry I've left out C symbol here, that should be gas, half Cl2 gas plus an electron. And then if you look from this step to this step obviously is splitting up that chlorine diatomic molecule into individual atoms. That will just be the atomization energy of chlorine there. So I've completed my cycle as I would do normally. So the final part of the question, using that below, calculate the enthalpy of formation for rubidium chloride. For this one, definitely it's going to be hard unless you keep track of the numbers. So I'm going to put them again on the cycle from what I know. The last enthalpy at the bottom, plus 685, that's going to go here. We'll also be given first ionization energy of rubidium, that is this change here, is getting plus 403. Enthalpy of atomization of rubidium is plus 81, that's the first step we did. The bond enthalpy of chlorine, again, looking a wee bit careful here. This is our first example where it doesn't actually match up perfectly. Think about this change here. We're going from half a mole of chlorine molecules into 1 mole of atoms. That is the atomization energy for chlorine, forming 1 mole. What we've been given is the bond dissociation enthalpy, which is breaking 1 mole of chlorine bonds. We're actually breaking half a mole of chlorine bonds here. Therefore, we need to half this value before putting it on our cycle. So it's going to be plus 242 divided by 2. You can do that all together, it'd be 121. Then, looking at the next step, electron affinity of chlorine is just 1 mole of chlorine atoms. That's just as expected. It's going to be minus 348. And then there's one missing bit of my cycle, which is this bit. Okay, so it's a variation because I have to manipulate it slightly differently. I need the change going from here to here. I need an alternative route for doing that change. So I can follow the arrows this way and then get down on this side. The only arrow I need to change is this last enthalpy arrow. It's pointing the wrong direction for that transition from left to right. So I'm going to flip it and change the sign of it, minus 685. So with all that background work done, what I'm going to do is just write out my numbers. So that change there, the formation energy is going to be plus 81 plus 403 plus 121, halving the bond enthalpy of chlorine, plus minus 348 plus minus 685. Typed it on my calculator, should come out as an answer of minus 428 kilojoules per mole. On to our final 2 questions. So this one's about sodium fluoride. It's a partially completed Born-Haber cycle. First part is complete the empty boxes by inserting the appropriate chemical symbols. So it's less completed than the last one was. Always been given as a salt, and always been given as split apart ions. That's just the last enthalpy going up there. So we have our standard transitions to get all the way up and then complete our cycle. So the first one is normally written as the formation enthalpy. So that's our standard state elements. So that's 1 mole of sodium, half a mole of F2. state symbols in. Then we will atomize our sodium first and keep everything else the same, so that's turning it into a gas. Then we'll do our first ionization energy of sodium, keeping the electron in importantly. And then we'll split apart our fluorine molecules into fluorine atoms. So Na plus as a gas, plus F individual atoms, plus E minus. And that makes sense because our final step here is putting that electron into fluorine, which turns into F minus. So 4 marks just putting those 4 boxes correctly. Using the data below, calculate the last enthalpy for sodium fluoride. So there's no kind of tricks here. It's just your standard working out your unknown lattice enthalpy. Okay, I'm going to be careful here. I'm going to put my numbers on just to be safe. So my first energy here is the first ionization energy of sodium. So that's going to be this step here, it's plus 496. The enthalpy of atomization of sodium is our first step, plus 104. Now, being careful here, bond enthalpy of fluorine, let's check this. This change is represented just by the atomization of fluorine because we're having 1 mole of atoms. So that's another example we're going to half this value. That value is for breaking 1 mole of fluorine bonds. We're breaking half a mole of fluorine bonds here. So I'm going to do plus 158 over 2. Electron affinity of fluorine, nothing wrong with that, so that's minus 333. And my formation of sodium fluoride is minus 574. Putting that all together, my lattice enthalpy will be, going the other way, sorry, I need to do my flipping step. So I need to go from here to here, so I need to flip the formation arrow like before and change the sign to plus, giving me my sum being plus 574, plus 107, plus 496, plus 158 over 2 is up to you if you do that calculation first, plus minus 333. If I put that all in together, I should come out with an answer of plus 923 kilojoules per mole. So our final question here is a wee bit longer. So we're given the Boron-Haber cycle for potassium iodide. It's more or less completely done. The last enthalpy is labelled, the other changes shown by letters A to E. So it's going backwards now. They've already labelled it. You just need to match it to the correct definitions of each change. So working our way down, the standard enthalpy of formation of potassium iodide, that's forming potassium iodide from its elements in their standard states, as written here. Therefore, it's going to be change E. First electron affinity of iodine, so that's iodine going to I minus, that is D. First ionization energy of potassium, that's K as a gas going to K plus, which is B. Then the atomization of potassium, that's going to be the solid potassium going to gaseous potassium, which is going to be A. Your calculation step, just for 2 marks, given all those values, what is the last enthalpy of potassium iodide? I'm going to put my numbers on, so my E value is minus 327.6. We've got decimal places here for extra fun. A, your atomization of potassium is plus 89.5. B, which is your first ionization energy, is plus 420.0. C, which is your atomization of iodine, plus 106.6. Final step, your electron affinity of iodine is going to be minus 327.6. So, putting that all together, our sum is going to be, need to flip this one first of all, make that plus. So my last enthalpy will equal plus 327.6 plus 89.5 plus 420 plus 106.6 plus minus 327.6. Typing in my calculator should come out as a final value of plus 648.3, keeping a decimal place in there. And it would appear I've made a pretty horrible mistake. I've transferred the wrong energy. That should have been minus 295.4. Apologies for that. So plus minus 295.4 will actually get you your 648.3. Now we've got some theory questions here at the bottom, which is unusual. Potassium chloride has a last enthalpy of plus 710 kilojoules per mole, and for potassium bromide it's 6 79, state 3 other enthalpy changes in Born-Haber cycle for these compounds which would be different. So what we're comparing here, we've got potassium iodide. It's talking about potassium chloride, potassium bromide. So we're comparing KCl, KBr, and Ki. So we're asking for 3 values that will be different. Now, some of them will actually be identical in these Born-Haber cycles because they've all got potassium. So atomization potassium, first ionization energy potassium will be identical. All the steps involving the halogen will be different just because they are different elements. So the only ones which actually involve the halogen in this would be the step here, where you're going when you're doing atomization of the halogen, your step here where you're doing electron affinity of the halogen, and your formation of the compound because it's a different compound in general. So your 3 different values would be, they did allow you just to write down C, D, and E. By giving them the first part, their formal names, the enthalpy of atomization, of the halogen, first electron affinity, shorthand, and the final one is the enthalpy of formation will be different. We then come on to this final question where you're asked to explain of those 3 enthalpy changes you've identified in C part 1, why are they different for each compound? I would actually say in my view this is a borderline completely unfair question. It's looking for a lot more detail than they imply in the question, but we'll just go through what the mark scheme says. They're looking for your justification about which will be biggest or smallest for each of these energies based on kind of your knowledge of chemistry up to this point. So the first one would be maybe your atomization of the halogen. A little appreciation you may have is that as you go down the halogen group, the bond actually becomes weaker because the molecules getting much, much bigger, the nuclei are further apart, there's less attraction. So what they wanted you to say was that the atomization for chlorine is going to be bigger than for iodine because of a greater bond strength or bond enthalpy. I think that's a bit harsh, but that's what they're looking for. Chlorine does have a stronger bond than iodine. The next point is the first electron affinity. That's maybe a wee bit fairer question. If you're comparing maybe your electron affinities for chlorine and iodine, the 2 extremes, because chlorine's a lot smaller than iodine, it's going to be much happier accepting electron because the nucleus is closer to the outside where the electron is being attracted from. So the first electron affinity, chlorine again will be bigger than, sorry, I'll go for single atoms, bigger than iodine because it is smaller and therefore a greater attraction to the outer shell. Final one is enthalpy of formation, which I think is a bit of a ridiculous question to ask. You've never had to look at formation values before. The formation value for KCl will be bigger than the formation value for Ki. Their justification for that is that chlorine is more reactive. Which I think is very hard for you to get, but again, it maybe was written as a question to sort of discriminate, maybe having to go beyond the spec a wee bit for this question. The more reactive an element is, the more exothermic that process will be, therefore more energy will be given out, which is what we see if chlorine or KCl is bigger than Ki. But again, don't get hung up if you find that one tricky. I think that's a very hard final question.